Good day everyone. Today, in this video, I'm going to discuss to you about Chapter 4, the response of first order systems. This is from the book Process System Analysis and Control by Donald Cognor and Stephen LeBlanc. So first, let's have a problem. From problem 4.8 from the book, the mercury thermometer of problem 4.6 is again allowed to come to equilibrium in the room air at 75 degrees Fahrenheit. Then it is placed in the 400 degrees Fahrenheit oil bath for a length of time less than 1 second and quickly removed from the bath and re-exposed to the 75 degrees Fahrenheit ambient conditions. It may be estimated that the heat transfer coefficient to the thermometer in air is 1/5 that in the oil bath. If 10 seconds after the thermometer is removed from the bath, it reaches 98 degrees Fahrenheit. Estimate the length of time the thermometer was in the bath. So let's first solve the problem. So let's have a first quick review for the chapter 4 of the book. First is we have y of s over x of s equals to 1 over tau s plus 1, or the tau which means time constant, tau s plus 1 equals to output ratio of output y over s over input, which is x over s. Now let's define first what is y of s. Y of s is the transform of forcing function or input, which is in deviation form, and also the transform of response or output, which is the x of s in deviation form. So in our problem, we have first the step change of magnitude, which is from in this equation letter A. So we have x of s, which is x of s in deviation form for the input, equals to a over s, and substitute this equation to x of s here. So we have y of s equals to a over s times 1 over tau s plus 1. And now in this equation, we're going to solve using the partial fraction, and you have to review your partial fractions. So we have an answer of y of s equals to the partial fraction of this equation, which is a over s minus a over s plus 1 over tau. And now we're going to review again about the inverse Laplace transform from this equation. So we have the y of t, the inverse function of this equation, equals to a minus e to the t over tau. So we have our first equation, number 1 equation, y of t equals to a times 1 minus e to the negative t over tau. So in the book, it also said that it is from the problem 4.6, and we have that Ts equals to 75 degrees Fahrenheit. And also in the problem, we have that the time constant for the oil is 10 seconds. So we have that time constant of oil equals to mc over heat transfer coefficient of oil, H of oil, A. And also for the time constant of air equals mc over h air times A. And now we're going to combine these two equations and using the ratio and proportion. So we have tau of air over tau of oil equals to h oil over h air, which equals to 5. So it means that we can get from the tau of air equals to 5 times the tau of oil, time constant of oil, which is 10 seconds. So 10 times 5 equals to tau air equals to 50 seconds. And now we're going to solve for this equation. So we have t from the first equation that we have that yt equals a 1 minus e to negative t over tau, which I change it to t over t to make it simpler. So we have t of t equals to a times 1 minus e to negative t over 10. And we have the step change of magnitude. Remember, step change of magnitude. We have that 75 degrees Fahrenheit then into the bath, which is 400 degrees Fahrenheit. So we have t of t equals to t1. Let's just say t1 equals to 325. 400 minus 75, 325. 1 minus e to the negative t over 10, which is the, by the way, this is for the oil bath. So that's why it is that the tau is 10 seconds. So let's have for the second equation, which is the Tmax. So what is Tmax? Tmax is the temperature at maximum of step function where the all bath will end, and also the start of air. So we have the Tmax equals to 75 plus 325. Adding just 75 of temperature, then adding the first equation here, T1, adding the T1, 325, 1 minus e to the negative T1 over 10. Still 10 because it's the air bath. Then Tmax, as I said earlier, start of the, end of the oil bath and the start of the air. So with that, so we have another equation that y over s equals to 1 over s times 75 minus Tmax times tau of air. Now, this equation involves for the air bath, air temperature. So we have now that 75 minus Tmax for the air temperature. So we have that. Now, let's change the time constant. It is not already oil bath but air temperature. So we have tau air s plus 1. So we have still the same process. We get the partial fraction, then we get the Laplace transform. We have I just shortcut it. Y over t equals 75 minus t max. This is our third equation. 75 minus t max times 1 minus e to the negative t2 minus t1 over 50. So this will be our third equation. As you can see from the equation that we have t2. As you remember, you have t2 equals to t1 plus 10 for that we have 10 seconds from the problem. So we are now determine the t1 for the problem by getting the Tmax. So we have, as you review in the problem, that we have that if 10 seconds after the thermometer is removed from the bath, it reaches 98 degrees Fahrenheit. So estimate the length of time that the thermometer was in the bath. So the length of time would be the T1, and it reaches 98 degrees Fahrenheit. So we have 98 degrees Fahrenheit equals to this equation from the third equation, 75 minus Tmax here, then adding the Tmax to get the answer for the Tmax. Tmax equals to 103. By the way, this is just using your calculator. We get Tmax equal to 103 to 103.09 degrees Fahrenheit. So we have now get the Tmax 103.09 degrees Fahrenheit. Now let's go back to how we get the T1, which is from the equation 2. So we use this equation to get the T1. So we already have Tmax, so here it is. So substituting this is the Tmax 103.09 equals to 75 plus 325. This is the equation 2. Then we have our final answer, which is T1 equals to 0.904 seconds. So to further understand the problem, let's have a graph. So first, as you can see, we have from the y-axis temperature at degrees Fahrenheit, we have 400, we have Tmax, we have 98, and we have 75. Then from the x-axis, we have the 0, the T1, and the T1 plus 10, which is T2 at time in seconds. So this is to explain or to use your imagination to picturize what really happened to the problem. So we have that oil bath temperature here, 400 degrees, constant. Then it was begin with the air temperature at this area. So we also have our Tmax since we have our time constant at 10 seconds. Then we have the end of the oil bath and the start for the tau 50 seconds for the air temperature. So we have our Tmax here. So let's just say that this is the graph here. Then we have the Tmax here. So at this temperature, at this peak, is the change of the air temperature. Then we have our 98 degrees Fahrenheit from the T1 plus 10 over T2. So This is just to show to you that what really happened to the problem, and I hope that this really this problem this graph will show you, and my solutions are helpful to you. So that's all. Thank you.